the physical and chemical properties of the elements. It is called as the periodic classification of elements and periodic trends in the properties. Now let us study these periodic trends or periodic properties of the elements. In these periodic properties, we consider the properties like atomic radius along with ionic and other radii, cationic and anionic radii, and isoelectronic species and different types of radius that we consider for the atoms. And also we consider the properties like ionization energy, electron gain enthalpy, valency, etc. First let us take this atomic radius. Atomic radius. First let us consider the definition for the atomic radius. Here under the atomic radius we have different types like covalent radius, covalent, van der Waals, then metallic, etc. Metallic radius, etc. Now among these, first let us consider this covalent radius. When we consider two atoms forming a molecule, then those two atoms are bounded by a covalent bond. Covalent bond is formed by the sharing of the electrons that we will discuss in the chemical bonding chapter. Assume that we have a homonuclear diatomic molecule like A and A. The distance between the two nuclei is taken as D. Then the covalent radius is defined as the distance between the two nuclei divided by 2, or half of the distance between the two nuclei which are bound by a covalent bond. Suppose you consider this hydrogen molecule. The two hydrogen atoms are bounded by a covalent bond by the sharing of electrons. Then you take the distance between the two nuclei of these two hydrogen atoms. Then if you take this distance as d, that is actually the distance between the two nuclei, internuclear distance. Then half of that will give rise to the covalent radius. So one way of defining this radius is half the distance between two nuclei which are bound by a single covalent bond. So this is one method to define this radius. There is one more method. Assume that this is the nucleus of the atom. This is the outermost orbit. Then in the atomic structure we have seen that at a particular distance there is a maximum electron density. Then beyond that one there is a gradual decrease in the electron density because of that wave character of the electron density. Wave character of the electron. It has a dual nature, that is the particle nature as well as the wave character. At a certain distance the effect of the electron density becomes 0. So another way of defining this radius is the distance between the nucleus and the place where the electron density becomes 0. So we can also define this radius as the distance between the nucleus and the place or the position, the place where electron density becomes 0. Electron density becomes 0. So earlier we used to consider the definition as where electron density is going to be maximum. But actually according to wave character, the distance between the nucleus and the place where the electron density becomes 0. That should be taken as the radius. There is one more type of radius called as the van der Waals radius. In case of this van der Waals radius, especially we use this van der Waals radius for the molecules in which the atoms are bounded by weak attractive force called as the van der Waals force. For example, when we consider this noble gas, for example, helium. When you consider one helium atom and another helium atom, they are not held by any chemical bond, they are held by a weak attractive force called as the van der Waals force. Because of the attraction between this nucleus and electron density and this nucleus and electron density of the other atom. So this is called van der Waals force. This van der Waals force holds these two atoms to a certain distance. Assume that this distance between the two nuclei is d. Then automatically this van der Waals radius is defined as half of the distance between the two nuclei. Now compare this covalent radius and van der Waals radius. Since here the weak attractive force existing between the two atoms, the distance between the two atoms is very large. That's why the covalent radius is always smaller as compared to the van der Waals radius. This should be kept in mind when we discuss about the radius of the noble gases. Now let us see how these atomic radii vary across the period. Before that one, let us consider one more definition, metallic radius. When we consider any metal in its crystal lattice, the distance between the two nuclei of a metal between the two atoms is called as the metallic radius. Assume that we have this copper in the form of a crystal lattice, copper solid. When we consider this copper in the crystal lattice, the distance between the two nuclei is called as the metallic radius. But mainly we consider this covalent radius. So let us see how this metallic covalent radius varies across a period. When we consider this second period elements, especially this lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine, we consider that neon as a noble gas. That's why for the noble gas we should take van der Waals radius rather than atomic radius, covalent radius. So when we consider this lithium, beryllium etc. in the second period, how this covalent radius varies, that we have to consider. When we consider this lithium, its nuclear charge is +3. But electronic configuration, if you look into the electronic configuration, it is 2s1. Beryllium +4, 2s2. Boron +5, 2s2, 2p1. 2s2, 2p2 with a nuclear charge +6. +7, 2s2, 2p3. +8, 2s2, 2p4. +9, nuclear charge is +9, 2s2, 2p5. Now when you look into the electronic configuration, the electrons are added to the same orbit, that is second orbit. When we consider the second period, the electrons are present in the second orbit. But gradually the nuclear charge goes on increasing from lithium to fluorine. As the nuclear charge increases, automatically the electron will be held with greater attractive force. That's why gradually this covalent radius, or we can generally take atomic radius decreases across a period. This can be explained due to two reasons. One is increase in the nuclear charge. The second one is addition of electron to the same orbit. Hence the radius gradually decreases. Now because of this addition of the electron to the same orbit and increase in the nuclear charge, the electron attraction between the nuclear charge and the electron goes on increasing. That's why the shell gradually shrinks. When we start from this lithium, from fluorine up to fluorine, there is a gradual decrease in the atomic radius. Now let us consider this down the group. Down the group. Here, when we consider this lithium, sodium, potassium, rubidium, cesium, and the last element is francium, which we take it as an radioactive element. Now, if you look into the electronic configuration, it's the 2s1. Here it is 3s1, 4s1, 5s1, 6s1. But a nuclear charge in this case, nuclear charge, here it is plus 3, 11, 19, like that it goes on increasing. When we consider the increase in the nuclear charge and also addition of the electron to the newer orbit, attraction between the nuclear charge and the electron, outermost electron, gradually decreases. Because of the distance between the nucleus and the outer electron goes on increasing, the attraction between the nuclear charge and the electron decreases. That's why down the group, atomic radius increases. This can be explained due to addition of electron to newer orbits. Second one, even though the nuclear charge increases, the attraction gradually decreases. And hence we consider the variation of the atomic radius across the period, which gradually decreases, while down the group there is a gradual increase in the atomic radius. So when you consider the total periodic table, from hydrogen to cesium there is a gradual increase in the radius. Hydrogen has got 1s1, lithium has 2s1, sodium 3s1, up to cesium 6s1. Gradually the new and newer orbits are added. That's why the electron is added to the newer orbit, and hence gradually attraction decreases but radius increases. When we move across the period, the lithium to fluorine, similarly sodium to that chlorine, potassium to bromine, gradually there is a decrease in the atomic radius. So overall, hydrogen is the smallest, cesium is the largest. In any particular group, alkali metal is the largest, while halogen atom is the smallest. Gradually there is a decrease in the radius across the period and increase in the radius down the group. Regarding the ionic radii, there are two types of ionic radii. One is cationic radius and another anionic radius. Along with that, we consider isoelectronic species, how the variation in the radius takes place when we consider isoelectronic species in the next video. Thank you.